Hello and welcome to this video about non-groups. In this video we'll be exploring some number systems that could have been groups but fail to become a group because they fail one or more of the conditions or axioms. We'll start off with the definition of a group, then examine one example of a group, and then some examples of number systems that fail to become groups, and find out why they don't, and we'll call these number systems non-groups. The definition of a group is a set of numbers that we'll call S, and an operation, usually addition or multiplication, that satisfies four axioms. The first of these axioms is closure. If two numbers are in the set S, then these two numbers with the associated operation is also in the set. The dot operation is used so we can say that A dot B is also in the set S. The second axiom is associativity. If these three numbers are in the set S, then this statement is true. The brackets show which operation is done first, which is the dot operation in this case. The third axiom is the existence of an identity element, which is usually called E in group theory. For any number in S, in this case which is given by A, there is an identity element E, such that this statement is true. The identity element dotted with A is A. It is true no matter which side of A it is operated on. Many viewers would recognize E as being 0 for addition and 1 for multiplication. And the fourth and last axiom is that an inverse element exists. For any element in the set S, there is another element in this set, such that it is the inverse of it. Applying the operation to this number and its inverse gives us the identity element E. Many viewers will recognize this inverse element as being minus A for addition and 1 over A for multiplication. So now to look at an example of a group, the real numbers with addition. It satisfies the closure axiom. The sum of any two reals is also a real number. That is, it is in the set of real numbers. It satisfies associativity. We won't go into too much detail in proving this. It has an identity element which is 0. Adding 0 to any number doesn't change the number. It has an inverse element, which in this case is minus A. So that completes the very easy proof that this is a group. So now to explore our first non-group, the natural numbers. This is the set of all whole numbers like 1, 2, 3, etc., and not including 0 or any negative number like minus 1, and addition is the operation being used. It very obviously obeys the first axiom, which is closure. Adding any two whole numbers that aren't 0 or negative will give us a whole number back, which is larger and so is still in the set. Associativity is also very obviously obeyed. Now to see if it has an identity element. The only possibility for the identity element here is 0, and that isn't in the set, so this axiom is false for this numerical system, so it is a non-group. We'll keep on exploring this numerical system to see how much it isn't a group. We'll look for an inverse element, which can't exist because the identity needs to be in the numerical system for an inverse to exist. But if 0 were in the set, then this axiom still wouldn't be true, because here is an example of an inverse that isn't in the set. In fact, none of the natural numbers has an inverse in the set. So this numerical system is a non-group which only satisfied 2 out of the 4 axioms. Now to look at this numerical system, which is the set of natural numbers with the number 2 removed from it. combined with the addition operation. We'll look if it satisfies the first axiom. And it doesn't. The sum of these two numbers is 2, which isn't in the set, so this axiom is false. It only takes one example to prove that an axiom is false. Now we'll explore the second axiom, despite already knowing that this numerical system isn't a group. We'll try these numbers in this equation. We'll firstly evaluate the left side of this equation, which gives us 7. When we try to evaluate the right side of the equation, we find that the number 2 finds its way into the expression, which isn't in the set, so that the operation can't be performed with a number that isn't in the set. So that is enough to disprove this axiom. Now we'll look to see if this set contains the identity element. And just like for the previous numerical system, the identity element isn't in the set, because 0 is the only possibility, and 0 isn't in the set. We can look to see if every number in the set has an inverse element, so as to satisfy the last axiom. And just like for the previous numerical system, none of the numbers in the set have an inverse, because all of the inverses are negative numbers. The non-existence of an identity automatically causes this last axiom to fail anyway, without having to prove anything else. So this numerical system is a non-group, and we may call it a complete non-group, because it fails all of the axioms. Now to explore the third non-group, which is Pythagorean addition over the reals. I call it Pythagorean addition because it resembles Pythagoras' theorem and is used to calculate distances between points. I'm using a small right-angled triangle as its symbol. We'll look to see if this numerical system satisfies closure. It obviously does. We'll just use an example to see it obey this axiom. We'll then look to see whether it obeys associativity. This is a bit tricky. We'll work our way through the algebra. We'll start off with the left-hand side of this equation and try to work our way towards the right-hand side so as to prove this axiom. We'll expand the term inside the brackets. Then we'll expand the next operator, and we'll get this nasty-looking expression. Squaring this expression inside the brackets gives us this expression. We can then manipulate this expression to be this. We can then contract this expression to be this. And then finally we get the right-hand side of this equation. And so this axiom has been proven to be true. Now to find the identity element E. Setting E equal to 0 should be the obvious answer. We'll evaluate one of the identity equations, which gives us this, so it is a left identity. It is also similarly a right identity, so an identity exists and is 0. Now to find the inverse elements. If we use the example of -1, we'll then try to find the inverse of -1 for this operation. Expanding this expression gives us this expression, which then gives us this expression. We can then see straight away that the only solutions for the inverses are I and -I, which aren't real numbers, so this last axiom isn't satisfied. So this is a non-group that satisfied 3 of the 4 axioms. It looked like it was almost a group, if only it could have satisfied the last axiom. Now to look at this interesting non-group, reals with parallel addition. This is the definition of parallel addition. It is used to get the total resistance of 2 resistors in parallel, and therefore uses this notation. The first axiom to prove is the closure axiom, and this is true for any 2 real numbers. Here's an example of 2 numbers that it is true for. The next axiom to prove is associativity. We'll prove this with algebra. We'll expand the left-hand side of the top equation. We'll sum these two fractions together. Then we'll simplify this fraction. Then we'll expand this expression again. Then we'll get this messy fraction expression. We can then manipulate it to be this, and manipulate it a bit more, and then contract this expression. And then finally we can manipulate this expression into being the right-hand side of the top equation. And now we've proven associativity. Now to find the identity element for this numerical system. We'll find the right identity by solving this equation. Expanding out this expression gives us this expression. Inverting both sides gives us this expression. Then we get this equation for the value of the identity. This identity value doesn't exist, at least not in the real number set. It can similarly be shown that the left identity doesn't exist either, so it doesn't obey the third axiom. Even though we've already proven that this number system isn't a group, we can still see if it is true for the fourth axiom, since we are exploring how much these number systems aren't groups, and which axioms they are and aren't true for. We'll check to see if every element has an inverse. It can't have an inverse if there isn't an identity, but we'll assume that it has one enough to check this axiom. We'll assume that E exists, so we'll have 0 on the right-hand side. We'll solve for B, which is the inverse of A. Manipulating this equation gives us this equation. We'll manipulate it some more. We can ignore the denominator of this fraction and set the numerator to be equal to 0. So now we've found the inverse, which is minus A, but it isn't really an inverse because the identity doesn't exist. So this inverse doesn't really exist either. This number system has now been proven to be a non-group. Now to examine the number system that is the real numbers with the exponent operator. We can write this operator with an up arrow, and it obeys the first axiom trivially. Now to check if it obeys associativity. We can use an example to prove that it doesn't. If we put the brackets around the first two numbers, we'll get this value. But if we put them around the last two numbers, we'll get a different number. Therefore this number system is not associative, and therefore not a group. Even though we've proven that this number system isn't a group, we'll still continue to check the last two axioms. We'll check to see if it has an identity. We'll try finding the right identity by solving this equation. The right identity does exist and is equal to 1. Now to find the left identity by solving this equation, which we can rewrite like this. The E here isn't the E which is 2.71828 found in other math, but the E found in group theory, commonly 1 or 0. If we substitute the right identity in here, it doesn't function as a left identity. So the left identity doesn't exist, and so an identity doesn't exist for this number system. Now to find the inverse element. The identity needs to exist for the inverse to exist. But we could try to find the inverse for the right identity, to at least see if the inverse for the right identity could exist. We'll write out the full definition for the inverse here. We'll try to find the left inverse of A, which is B. We'll rewrite this equation. The only way that this could be true is if B, the inverse, is equal to 1. So this means that if A is not equal to 1, then its left inverse doesn't exist. We'll try to find the right inverse of A. We'll rewrite this expression. And so the only way that this expression could be true is if A's inverse is 0. So the right inverse doesn't exist either. So the inverse doesn't exist, and even right and left inverses don't exist, even for only a right identity. and so this number system is definitely not a group. The last number system that we'll look at is this one, being the set of all natural numbers and all of their inverses with the multiplication operation. We'll check to see whether it satisfies closure. We'll use this example to show that it doesn't. In fact, most of these products aren't in the set. Now to see if it satisfies associativity. Here's an example of where it isn't true. If we multiply these numbers so that the brackets surround the first two numbers, we get this number. But if we surround the last two numbers with brackets, then we get 3/2 in the calculation, and because it isn't in the set S, the calculation fails, and this causes this axiom to fail for this number system. Now we'll have to search for an identity. This axiom succeeds because 1 is in the set, and is the identity for multiplication. And finally we'll have to find out whether an inverse element exists for each number in the set. This axiom is true for this number system because each number in this set has an inverse. So this is a non-group that satisfies 2 out of the 4 axioms. In fact, it is a strange number system because it fails the first 2 but succeeds with the second 2. Now to explore some of the reasons that number systems fail to satisfy the group axioms, and thus fail to become groups. We'll firstly look at closure, why closure fails for some number systems. Holes and upper bounds cause it to fail. Usually applying the operation to a couple of numbers tends to return a larger number, so upper bounds can fail when lower bounds don't fail. We'll look at associativity next. This can fail when the operation is unsymmetric, like the exponential function, where the numbers perform different functions on either side of the operand. What causes there to be no identity? If a known 0 or 1 isn't in the set, or if the identity became infinite, like in the case of parallel addition, this can cause it to fail the identity axiom. And finally, what causes there to be no inverses? If there is no identity, there cannot be inverses. And lower bounds cause there to be no inverses, because inverses are generally on either side of 1 or 0, and this boundary can cut off all of the inverses from their corresponding numbers greater than 1. So I hope that you have enjoyed watching this video and have learnt something from it. I wish you all the best in your quest to learn abstract algebra. Please click like and subscribe if you enjoyed this video. Please leave all of your thoughts and ideas in the comments, and thanks for watching.